And today's review, be sure, again, just like exam 1, make sure you review all the quizzes, all the homework, all the in-class problems, because everything that's listed here, I don't have everything. Okay, this is just kind of like an overview. Now, I also moved up from the handout for today. I moved up some questions because when we have to make those ICE tables, that's a lot of work. But those points, that's a 10-point question. That's the same as some of these conceptual questions. So I think you should, get the easy ones, get the easy points first. It's not, if you're going to screw up on something, screw up on the quadratic formula question. So I'd like to just run through not how to solve these. I mean, you're going to work on those together to get through them. I just want to run through and make sure everyone's got the general idea how to solve this kind of stuff. For example, on this very first one, you have to write equilibrium constant expressions. What's it about? Solids and liquids. And you raised everything to the, what was it called? Their powers, raise them to the stoichiometric coefficients. Yeah, okay. Something like, okay, completely go to product. You just have to get used to the terminology again. Remember, completely goes to product means the reactant's almost completely reacted. That means there's hardly any reactant left. When you reach equilibrium, it's all product. So how can you pick a reaction that says, oh, I have all product, or the reaction goes to completion? All you do is look at the K. You want K to be really, really... Now, K is products over reactants. You want K to be really, really big, because K is products over reactants. So any reaction with a huge K, it's all product at equilibrium. The reaction goes to completion. Let's see, how about something like, okay, writing conjugate bases and conjugate acids. If you're going to write a conjugate base of something, what happens to this formula? You have to take away a hydrogen, and then what do you do to the charge? Add a -1, right? If you want to write the conjugate base, and they give you the conjugate acid, you have to take away an H, and like Juan said, add a -1 to the charge, because you're removing an H+. If you want to write a conjugate acid, right, they gave you the conjugate base, you have to write the conjugate acid. Now, what happens to the chemical formula? Add an H, and what do you do to the charge? Add a +1. Whatever you get, you get. So you have to add an H+. And then we had things like this, where we had to predict the direction of the reaction, and we also had to write the product. Now, first, let's go over the final answer. How do you know which way to draw the arrow? Once you figure out what the products are, acid. And you always pretty much figured that out how? Looking at the table. Okay. But there's other homework question, and it may not be in the table too. There were ways that we talked about to figure out, oh, this acid's stronger than that acid, and they're not in the table. More oxygens was one. What was another one? More hydrogens was another one. My goodness, just as he's nailing level 3, right? And if it was bigger, right? And that's for the group idea in the periodic table. The bigger atom had a weaker bond with the H, so it was a stronger acid. Those are the 3 ways. Okay, so we draw the arrow towards the weaker acid. Great. How do you predict the product? How do we go about figuring this out? Yeah, there were always the conjugate acids and conjugate bases. But where do you start? To me, that was the trick. Where do you start? Find something that's only a base or only an acid. It doesn't have any choice, right? So, in other words, if it doesn't have any hydrogens at all, it has to be a fully protonated. I don't know what other word to use. It has the maximum number of hydrogens it possibly can get. It's fully protonated. For example, the only way to know this is if you remember your polyatomic formulas. sulfate had a what charge? SO4 has a, that means it can only have, what's the maximum number of hydrogens? 2. So if you have H2SO4, it has to be an acid. Okay? So if you look at this question, here's our reactants. Which one do you start with? Which one determines everything? The F. The F minus has to be a base. Good. F minus has to be a base, so you're going to write its conjugate acid on the other side. The HSO4 minus has to be a acid then, so you write its conjugate base on the other side. Okay. How about, oh, Jessica already answered this. What's going to be the deciding factor? Pretend they're not. I'm sure they're not in the table, honestly. Which one's bigger? It's got to be a which one's bigger question, because they both have the same number of hydrogens. There's no oxygens. It's got to be a bigger question. Something like this. What are the concentrations of hydronium hydroxide in 0.045 molar perchloric acid? Just starting out, everyone hopefully is on the same page and realizes H3O plus is really just what? It's really just H plus. Because you should have this equation sheet staring at you when you're doing the homework, doing the quizzes, preparing for this exam, doing this whole review. Because you have to use the equations to figure this out. Right? So where would be the starting point? Something like this. And you've got the equations, but the H plus has to be what? 0.045 molar. Because HCl4 is a, well, strong acid. Strong acid. And that's the only type of question I can give you right now anyway. But exam 3, no, they're going to be mixed in. So that's why it's good to recognize that this only works for strong acids. And then you use the equations to get the hydroxide. Again, something like this. The pH is 11.63. They want to know the hydrogen and hydroxide ion concentration. So pretty much have to use the equations again, right, and figure it out. I bet you it's going to be multi-step. There's easy ways and there's hard ways, but you get the same answer however you do it. Okay. Now we had whose principle? Start with an L. Le Chatelier. Okay. And there were easy Le Chatelier questions, and there were hard Le Chatelier questions. If they added a reactant, the equal product, because now you have too much reactant. If they remove a product, it's going to shift towards the, they remove a product, now you don't have enough product, it's going to shift to the product, right? If you remove a product, now it's like a hole. It's shift to the product. If you remove a reactant, okay? So that covered a lot of the questions, but it didn't cover this one. What are the general temperature and pressure conditions? Now, how did we do this? Let's think about the temperature one first. It made sense, didn't it, when I said, hey, if you add a reactant, it's going to shift to the product. That makes sense. So to me it makes sense. When we do the temperature idea, just write the word what as a reactant or a product? Heat. So you don't think of it as heat. You think of it as a reactant or a product. Right? So you write the word heat on the reactant or product side. You're going to write it on the product side when delta H is negative. You're going to write it on the reactant side when delta H is positive, endothermic. Okay. And that's how we figure out the general temperature. The general pressure conditions, though, right? Because you can add stress to a system that involves gases. You can reduce the pressure. The system has to respond to remove that stress. So having too low of a pressure, that's the stress. Having too much pressure, just, I don't know, maybe you have this piston or something in there, right? Those are stresses. The system has to respond to it. So with pressure, we had to figure out the number of what molecules on each side. It was gas molecules, because gas is the only thing that can exert pressure. Okay? Same number of gas molecules on each side, it doesn't matter what you do to the pressure. There's no way the system can respond. If one side has less gas molecules than the other side, that means that there is a high pressure side. One side has more gas molecules. Has a high pressure side. Whatever side has more gas molecules, I call it the high pressure side. I kind of underline the whole thing. Oh, that's the high pressure side. Okay. Then you just do the experiment. Okay, what happens if I crank up the pressure? Well, that means I have too much pressure, the system has to relieve it. It's not going to shift to the high pressure side then. It's going to go to the other side. Okay? So if you could, how could you answer this question? Right? How could you answer that question? Okay, let's write the word heat somewhere first. Write it over here. All right, and write it over there. Oh, I can't see it. See it? Okay. Write it over there. Now, so how do you answer the temperature? Now we want, what do we want? We want optimum production of nitrogen. So that's a product or reactant? The product. We want optimum product. So, what should you do with the heat? Remove it or add it? If you're going to add it, right? And you want too much reactant, so it shifts to product. That means the temp's got to be really, really high. You want too much heat. So high temp. There's our answer for temp. Pressure. Okay? Pressure. How many gas molecules on this side? 4. On this side? 3, right? 2 and 1, 3. Okay. So which side has high pressure? Yeah. This is my high pressure side. Okay. And I want optimum N2. So if I crank up the pressure, just pretend the answer is high pressure. Is that what we want? Because it has to relieve that high pressure. First off, can it? Is there a different number of gas molecules on each side? There are. So it can relieve pressure. If you crank up the pressure, it's not going to shift to the high pressure side. That's generating more pressure. So it's going to shift away from the high pressure side. So is that what we want? Yeah. So you want high pressure. High temperature and high pressure. Okay. Because we wrote the word. Yeah, we wrote it on the reactant side. Okay. Oh, what was that? Okay. Now we have this next question here. Whoa. It's really messing up here. Can't see it too well. Okay. EX1A here. Looking at this. Look at that. Why didn't it take it? Okay. We had these ice table questions. And remember, you make the ice table. What are all your answers? In the E row. Because they're always after equilibrium composition. What are the concentrations? At equilibrium, what are your answers? What are the final equilibrium concentrations? What's the molar composition? Everything's at equilibrium, though. So all your answers in the E row. Now, your E row has what variable in it? X's. Okay, so once you figure out the X, you just substitute them back into the E row and you have all your answers, right? Now, there's an easy way to find the X, and there's a hard way to find the X. The easy way to find the X is when they give you what one of the answers are. What one of the E, in the E row, of all the reactants and products listed in your ice table. The easy way is when they give you one of those, right? If you look at this question right here, this first one, look at that. They tell you equilibrium mixture containing this. They give you one of your answers. So you do the whole ice table. And then whatever you wrote under SO3, you just set it equal to this. And that's how you get your X. And then you substitute it into all the other you wrote in the E row in your ice table. So you have them all. Okay, do you see that? They give you one of the answers. Big difference between that one and this one. Look at that. They don't tell you anything. They don't tell you any of the final answers in that question. But nothing changes. You still got to do an ice table. Right? So you still do the ice table. It's just that now you've got all your X's in your E row, which is where all your answers are. You got to keep going. You can't quit. So the only next thing you can do is write this, where is it? Here, at KC. Right? Products over reactants. But realize, oh, it's KC. All those K expressions are written in terms of not moles, moles per liter, big M. So when you do that ice table, I think that's a lot easier not to just put moles in there, but to put in the moles over liters. Put in big M units in that ice table. Oh, you're going to forget. Okay? So pretty much, I think, whenever they give you volume, you have to put it in terms of concentration right off the bat. If they give you volume, it's the same thing, right? If they don't give you volume, you don't have to worry about it. But if they do give you volume, just make an ice table with concentration. Okay. So, I think we should work. You guys work together on these. I'll walk around and help you out, and realize you can come in. I'm going over this again at 11, so you can sit in here, do it, go over it again. Lab today, you can come into room 212 Met from pretty much 12 to 3 or 4 p.m. Come in and study some more. Thursday morning, 8:30 to around noon, come in and ask some questions. Again in 212 Met. So go ahead and work through these. I'm going to shut this off.